Hello, we are from ChemPraxis, and in today's video we will be covering Physics Paper 3, Variant 4, May-June 2013, Question 2. In this experiment, we will be investigating how the speed of the water flowing through a tube depends on the tube length. Now, before we proceed, let's look at what is provided for us for the experiment. So these are the apparatus that are provided for us for the setup. As you can see, we have a flexible plastic tube, plastic syringe, modeling clay, a round tray, vernier calipers, meter ruler, a beaker full of water, a stopwatch, boss, clamp, and a stand. Okay, so back to the question. Now we will need to measure the internal diameter of the flexible tube. So now, we'll use the vernier calipers provided to measure the internal diameter of the tube. How do we measure it? We can use the internal jaw of the vernier caliper and put it into the inside of the tube and push your thumb grip back, like how would you measure a regular object, until the flat side of the internal jaw reaches the walls of the inside of the tube. Then we can fix the position by turning the locking screw. Then we can pull the internal jaw of the vernier caliper out of the tube and read the scale. So we'll first look at the position of our zero mark of our vernier scale, which is the smaller line of the scale right here, to our main scale, which is the larger scale right here. As we can see on the main scale, the reading is somewhere in between 0.3 and 0.4 cm. And the position of the zero mark is nearer to the 0.4 cm line. So we will know that the reading will be somewhere more than 0.35 cm. Hence, we can start looking at the vernier scale from 5 onwards and see which of the lines on the vernier scale will align perfectly with any of the lines on the main scale. So as we can see, it aligns perfectly with the number 8. Hence, we can say that this reading will be 0.380 cm. The reason for the 3 decimal places is because the smallest unit that the vernier calipers can measure is up to 0.02 mm, which is 0.002 cm, which is 3 decimal places. So now that we have taken our measurements, we will need to take the average of the 2 diameter measurements we took to get our accurate D, which is 0.390 cm. Then we can calculate the percentage uncertainty in D. There are 2 ways to do this. We can use the half-range method, or we can use the absolute uncertainty of the measuring equipment, which is 0.02 to 0.05 cm. We'll be using the half-range method this time as we already have 2 readings of D, and we will get 3%. For the significant figures of your percentage uncertainty, we always follow the smallest significant figure of our substituted values. Now, moving on to the next question, we will need to remove the plunger from the syringe body and measure the length L of the flexible tube using the meter ruler, which I have done, which is 20.0 cm. Then we will need to push the nozzle of the syringe body securely into one end of the flexible tube and assemble the apparatus shown in figure 2.2 and attach enough modeling clay near the bottom of the tube to make it hang vertically. Then we will need to fill the syringe body to the top with water, and as the water level falls in the syringe body, find the time taken for the level to fall from the 40 cm cube graduation to the 10 cm cube graduation. So we have set up the apparatus right here, and following the instructions given, we will pour the water into the syringe body until the top and start the stopwatch when the water falls to the 40 ml level, and stop the stopwatch when it reaches the 10 ml, and we get 3.84 seconds. Make sure to record the time to 2 decimal places as it is the smallest unit that the stopwatch can measure. And remember, for any time measurements, we will need to repeat the experiment at least once to find the average time. So back to our question, we can now record our readings. So after finding the average, we get 3.815 seconds. Now moving on, we will need to calculate the average speed V of the water in the tube using the relationship given right here. So simply we can just sub in our values and we will get 65.8. Then for the significant figures, we will be using 3 as it is the smallest in our substituted values. Now moving on to question D, justify the number of significant figures that you have given for your value of V. Now we will write as D had 3 significant figures while T has 4 significant figures. Hence, V follows D as it has the smallest number of significant figures. Now moving on to question C, we will need to detach the tube from the syringe body and reduce its length by cutting it in half. Then we will need to repeat the experiment we did in question C with one of the shorter tubes, which I have collected the data here. Now moving on to question F, it is suggested that the relationship between V and L is this equation, where K is a constant. So we will need to rearrange the equation to where K is the subject. Then we can substitute in our values, so we get 216 and 253, which we will need to round it up to 3SF as it is the smallest significant figures of our substituted values. Units are not a requirement to be written in your answer, but you will not be penalized for writing it. Now moving on to question F2, it is suggested that the percentage uncertainty in the values of K is 15%. Explain whether our results support this suggested relationship. So this is a very common question. We will need to calculate the percentage difference between our values of K and compare it with the percentage uncertainty given. So this is the formula of the percentage difference which you will need to memorize. We will sub in our values, which we will get 15.8%, which is larger than the percentage uncertainty. Now we can write our conclusion. Remember, if your percentage difference is larger than your percentage uncertainty, then we do not support the relationship. If our percentage difference is smaller than the percentage uncertainty, then we support the relationship. Take note that it does not matter how large your percentage difference is as long as it is larger than 0%. As long as you write the correct conclusions and calculations, you get the full marks. So for this question, we can write as the percentage difference is larger than the percentage uncertainty, hence the results do not support the relationship. If your percentage difference is smaller than your percentage uncertainty, hence you can write as the percentage difference is smaller than the percentage uncertainty, hence the results support the relationship. Now for our final question, which is finding 4 sources of uncertainty or limitations and their corresponding improvements. Always remember that all the uncertainties that you will need to identify are the ones that you will encounter when trying to take measurements. Now you may pause the video to think and write down the possible uncertainties and improvements. Alright, now so for the first uncertainty and its improvements, you can always write this in any of your papers, so you'll need to memorize this. You can write, 2 readings of K are not enough to draw a valid conclusion. And its improvement is, take more readings and plot a graph, or you can write, take more readings and compare K values. For the second uncertainty, you can write, large uncertainty in T because T is small, or tube distorts when measuring D. Always identify what is hard to measure first and include a reason. If not, you will not be awarded with marks. And for the improvements, you can write, measure outside diameter and wall thickness, or measure an image showing the cross-section and the scale, or using traveling microscope, or measure volume and calculate D. You can always suggest a formula or directly draw a diagram to show them how to get a more accurate measurement if you do not know how to describe them. For the third limitation, you can write, tube not straight, so difficult to make tube vertical, or tube not straight, so difficult to measure length. And its improvement is, you can suggest, tape to a straight rod, or increase attached mass. So for the fourth limitation, you can write, difficult to judge moment, or simultaneously operate stopwatch when level reaches syringe graduations. And for the improvement, you can say, use video with timer in view and playback frame by frame, or collect water from a time interval and measure volume, or use light gates and timer with practical detail, or use different diameter syringe with reason, or use position sensors above water surface. Now, there are two additional uncertainties that we can write. The fifth one is difficult to see water level, and its improvement is use colored water or dye, or use a clear syringe, or view against black background. And for the sixth uncertainty, we can write clay stretches or squashes tube. For the improvements, we can write measure length after attaching clay to see if it's really increased or decreased in length after the attachment of modeling clay. So this is the end of the question. If you liked the video, don't forget to like, share, and hit that subscribe button. This is ChemPraxis, and thanks for watching.